Welcome to the discussion of the third theoretical exercise, example solutions. So we've mostly talked about synchronization in this example and deadlocks. And first we started with a question about deadlocks in real life. So we've already seen the example of a crossroad with like roads going in all four directions without any traffic lights or any signs indicating which car is allowed to go first. So we've seen if a car comes from each of the four sides, then we have a deadlock here. And the first question was just to have you think about a number of other examples of deadlocks in real life that are not related to computers. Well, actually, I found one other related to computers that's funny enough, so I included it here. So first thing is another traffic example. So if you have a narrow bridge, so for example, a one-lane bridge connecting two-lane roads, if there's a car from both directions that has entered, then, well, this is obviously a critical section. So you usually have some semaphores. So semaphore is also maybe just a word for a traffic light in this situation here. And you can actually resolve this. So one of the cars actually has to back up in order to make the way free for another car. Now, a computer-related thing I found is a fun effect on some older PCs. So if a keyboard is not found on older PCs, the BIOS will complain and ask the user to press F1 to resume, which is a bit difficult if no keyboard is connected, obviously. And maybe some other problems. So this is an example I found on the internet. So a problem of an introverted person. Like, I don't really like to talk to people before I get comfortable with them, but I don't get comfortable with a person before I've been talking with them for a while. So essentially, here, these two conditions exclude each other. So we could also see it's a deadlock. But of course, in real life, the definition of a deadlock is a bit more, imprecise than what we use in computer science, obviously. So let's continue with computer science examples. And the second question of the exercise was, let's assume we have a resource deadlock in the system and we figured out how to find out resource deadlocks. So we find a circle in the resource allocation graph here. So that's what's marked in red here. So we have three resources, T, U, and V, and three processes, D, E, and G, and they are in this circular dependency. So we've seen incoming arrows to a process means this resource is allocated to a process, outgoing arrows from a process, so these are the ones in the circles. An outgoing arrow means there's a request that can be fulfilled or cannot be fulfilled. So here D holds resource U and requests resource T. Resource T is held by process E, which requests resource V, and resource V in turn is held by process G, which, and this closes the circle, has an outstanding request for resource U. So if none of these is willing to give up the resource request, and we've seen the three necessary conditions and the first condition that we have a circle in that graph here to create a deadlock. So if none of these can or is willing to give up this request, then we have a deadlock and we cannot continue. And the question here is actually, can there be other processes that are impacted by such a deadlock situation, by a circular chain? And we see it in the example here. So this is process B, which also requests resource T. Resource T is held, so process B also cannot allocate it, like process D. So essentially, process B is not part of this circular chain here, but still is impacted because it cannot proceed before it can get access to resource T. So here we have the situation that many more processes could actually be affected by one deadlock that shows up in the system. And we had a bit of more of deadlock questions here. We had something regarding databases, but it's also just parts of files. Oops, excuse me here. So we have two processes, A and B, and each of those need three records, numbered 1, 2, and 3 of a database. And of course, we have exclusive access to these records. That's what we assume. And if both A and B request the records in the order 1, 2, and 3, then deadlock is not possible. But if B, for example, uses a different order, like 3, 2, 1, then a deadlock can occur. And the idea of this question was actually to take a look at the orders of three resources. So you have the factorial of 3, so 6 possible combinations for requesting these resources. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and so on. And what was interesting to us is which fraction of all combinations is guaranteed to be deadlock free. So which order of allocations can you perform that can that we can show that they don't lead to to a deadlock. So let's just assume that process A starts to request records in the order 1, 2, 3. So if the first allocation of process B is also 1, then either process A continues if process A first gets access to resource 1, or on the other hand, if process B first gets access to resource 1 granted, then process B will continue. And in turn, the other one will block. So this situation is always deadlock free, since the winner can now run to completion without interfering with the other. And of course, we have to assume that these resources are then given back to the system when the respective process terminates. So let's look at the other combinations here. So for other combinations here, we can similarly reason about these and show that they can lead to a possible deadlock. So 1, 2, 3, 1, 3, 2 are deadlock free. 2, 1, 3, 2, 3, 1 can lead to a possible deadlock. 3, 1, 2 and 3, 2, 1 can also lead to a deadlock. So only 1/3 of the cases is guaranteed to be deadlock free here. All right. So the next question was about one of the algorithms. We took a closer look at the banker's algorithm. And we were asked, or you were asked, to consider a system that uses this banker's algorithm to avoid deadlocks. So we have a scenario for which at some point in time, a given process P requests a resource R, but this process B is denied the resource, even though R is currently available. So the question was asking you to try to understand this algorithm, and the question was, like, if the system would allocate resource R to process P in that moment instead of denying it, would the system necessarily deadlock in all situations? And the answer is no. And the reason is that an available resource is denied to a process that requests it using the banker's algorithms if there is just a possibility that the system may deadlock by granting that request. So we have no guarantees. So it would actually be possible to grant this resource R to process P in this situation, but then we have an unsafe state. So essentially it could happen that we have a deadlock, but we don't necessarily have a deadlock as a consequence. So this is the difference I wanted you to think about. So it's certainly possible that the system may not have deadlock if that request was granted, but it's not guaranteed. And since we want to have safe states in our system, then we usually deny the granting of this resource R to a process in the banker's algorithm. And the remaining questions now were about software development, the software development process. And one of the things that causes lots of trouble in C code is the C preprocessor and especially macro processing. So here we have a very simple definition of a macro called square of x. So x is a parameter. And whenever we write square of something, so not necessarily x, but a number or whatever we can put inside of these brackets, then this is replaced by opening bracket, then whatever is inside of the original brackets, then a star or multiplication sign, then again, whatever is contained inside of these original brackets here and a closing bracket. So obviously, that would be the naive implementation of a square function that just, well, returns the square of a given number, for example. And the interesting thing is the C preprocessor doesn't know anything at all about what x is. So you could write square of 4, and it would operate on integers. You could write square of 3.14 something, and it would operate on float numbers. That's a nice thing about it, but that's also very problematic, just because the C preprocessor doesn't know about semantics of C, it doesn't know about operator precedence, and so on. So it really only performs very stupid syntactic text expansion. So it means whenever it encounters square opening bracket x, closing bracket x, closing bracket, then it just takes this text x that's between the opening and closing bracket and just copies it into wherever x appears on the right hand side. So if we have square of 2, we would get 2 times 2. This would be evaluated to 4. That would be fine. But of course, we are also allowed to put an arithmetic expression inside of the brackets. So we could say square of 1 plus 2. And this is stupidly expanded to what you see here, 1 plus 2 times 1 plus 2. Now the problem here is that in this case, the arithmetic precedence rules of C apply. So multiplication is evaluated first, even though it looks different. So the first thing that's evaluated is 2 times 1, which is 2. And then it adds 1 in the front and 2 in the end. So the result is 5 instead of square of 3, which we would expect it to be 9. And this is just one of the very many pitfalls you have with the preprocessor and macros. So I would recommend, for example, looking at the bit of an older GCC documentation here. I guess there's also a more recent one, but that's perfectly fine. And this describes the pitfalls with C preprocessor macros that can occur. So essentially, you would solve this problem by just putting round brackets around the axis on the right-hand side of the define. That would work, but there are many more problems which are listed here, which I'm not going to discuss for this exercise. But this just means if you use these preprocessor functions, you really need to be careful. The next thing we discussed were ELF segments. So we've seen ELF is the executable binary format for most Unix systems, excluding Mac OS X. Windows uses another format which is relatively similar called ECOF. And we've seen tools to analyze the ELF file. So an ELF file is not just executable bytes and data bytes which are copied into memory, but ELF files have a format describing in a header several sections and properties of that file. And there's a tool called readelf, and if you call readelf -S on a program proc, then you get information about the sections contained in the ELF file. And we've seen the different sections. So we've seen a text section, which contains the executable code in binary. We've seen a data section, which includes all the initialized global variables. We've seen a BSS section, which contains the uninitialized global variables. So BSS, if you check for this, usually has a size of 0 in the ELF file because it's all just variables initialized to 0 automatically. That's a C convention. All global variables are initialized to 0 if they're not initialized manually. So essentially, we have all these sections, and there's a number of additional sections like debug symbols, stack sections, and so on. So here we took a look at just one of the sections, the data section, so initialized global variables here. And the question was like, if you have an output like this, and you know that you only have global int variables in your program, and let's just assume each of these variables uses 4 bytes. The question is, can you tell how many global int variables are actually declared in the program? Now, the first thing you have to look at is the size of the segment. This is the number on the last line of the output to the left in blue. So this is lots of zeros and then 1 0. So this number is always in hexadecimal. So hexadecimal 10 is decimal 16. And this size is always in bytes. So you know the data section has 16 bytes of contents. So with each integer variable being 4 bytes in size, you know it can hold a maximum of 16 over 4, so 4 integer variables. Now the problem is that there's something else which is on the far right hand side of the readelf output, and this is this align information. So align means the minimum multiple of bytes that such a data structure and of course the following ones are allowed to start at, and this is 8 here. And so 8 is obviously twice the size of an integer variable here. So what this means is we could well have 4 int variables here, but even if we only had 3 int variables here, that, due to the alignment requirement, 3 int variables would use 12 bytes, but the alignment means that the next address needs to be divisible by 8. So we need to pad this. We need to fill in some extra information, some additional 4 bytes, so that the section coming after data is actually aligned to 8 again. So essentially, what could happen is that the data section also only contains 3 integer variables. So you can't really tell if it's 3 or 4. But it's not 2, because 2 variables would fit an 8 byte. So then we'd have a data section that would only be 8 bytes in size. So without further investigation, we cannot say if there's 3 or 4 global int variables declared, but of course there's other tools to help us, and for example NM, the name tool, gives us the output of the symbols contained in a program. So usually when you compile a program, the compiler or linker then adds the symbol information, so you can have variable names that you declared in your program, and these are associated to addresses in memory. There's a tool in Unix to actually get rid of this symbol information. This makes it a bit harder for someone trying to hack or reverse engineer your program. This is called strip. So strip just removes all this debugging and symbol information from a binary. This has 2 advantages. First, the binary gets smaller. Second, well, there's no symbol information anymore, so you don't know the names of variables or functions. You just have hex addresses. So somebody trying to reverse engineer your program wouldn't really know what's going on, but of course, when you want to debug it, you keep the symbols in. So ELF symbols were the contents of the next question here. So we have a very simple and useless C program that declares 2 global int variables here, and then has a main function that also declares 2 other int variables here. And the question was, which ELF segment will variables foo and bar be located in? So they're global variables, so they're not declared in the context of any function, but on the top level of our C source file. And they're not initialized in the source code. So they're not initialized to int foo equals 42 or something like this. An init inside of main wouldn't count here. So what this means, and as a C convention, they're automatically initialized to 0 by the C runtime, by the CRT0 runtime that we've seen. And thus we are not actually storing them in the data segment, because storing zeros just wastes space. But we have this separate section or segment I just mentioned, the BSS segment. This is an old term which originally stood for base store segment. It doesn't have any real meaning today anymore. It's just called BSS for historical reasons. So this actually saves space in the executable, because we only have to store addresses in BSS. We don't have to store it with the executable, but we have to allocate a memory range for BSS, which is then just filled with zeros when we start the program. If we had a global variable int bats equals 42, then this would be stored in data, because we need to have this information that this variable is initially 42 when the program starts, so we have to load it along with the program. And the second question in this task was, when I run the nm command on the compiled binary that results from compiling this program, we cannot see variables a and b in the command output. And the question is why. Now, these are local variables in contrast to global variables. So local variables are put on the stack. So they cannot have a fixed address in memory, because we are allowed to call each C function recursively. And this includes main. Though everyone might think that main is a very special function, it's not very special in this respect. You could call main recursively. It doesn't make much sense in most cases, but you could do it. And this means that for each level of recursion, you need a separate copy of these variables here, because otherwise you'd overwrite the values of a previous recursion level, which then would lead to incorrect data being processed by your program. So A and B are on the stack, so the only thing they have is a fixed offset from the current stack frame. But of course, this is not a fixed address, because the stack moves downward and upward in memory as required by your program execution. So this is why these variables are not contained in the NM output, just because we can't see them here. And yeah, you could call main recursively. It's just a regular function. There's nothing special in this respect. So this was all for today's exercise. Thanks for listening. I hope you got a bit of an insight into more about deadlocks and synchronization, and on the practical side, a bit more about how all this program compilation, execution, and things around it, so debugging and symbols actually work. That might be useful later on when you're running projects and need to debug stuff. So thanks for listening, and until next time. Bye.